Hi, and welcome back. So today we're going to be starting to add some other elements to our carbon skeletons. And when we do that, we have to start thinking about these things we add as functional groups. These are groups of atoms where the sum is greater than the parts. So if you have a nitrogen atom bound to a carbon, and that nitrogen atom happens to have two other atoms, they could be hydrogen or they could be other carbon atoms bound to it, we call this an amine. If we add an alcohol to that carbon, or if we add an oxygen to that carbon, and put on that oxygen another proton, we call that functional group an alcohol. Okay, so I want you to recognize that when we draw these in line structure form, the carbons still end up being drawn as just lines like this, but we always add in the heteroatoms, that is, atoms that are not carbon. And we not only draw in the nitrogen in this case, but we also draw in the number of hydrogen atoms that are bound to that nitrogen. So it's important to recognize that the drawing here is not the same as the drawing above. And if you looked at the atomic formula of that, you'd see that there are 3 carbons, because it's propane based. There are 9 hydrogen atoms, and a nitrogen atom here. If we drew it the way that I've circled at the bottom, that shows that there are 7 hydrogens bound, so they are not the same. So when we look at trying to figure out bonding patterns, we can recognize that there are a different number of bonds depending on the atom involved. So carbon, as we talked about before, typically has 4 things bound to it, 4 other atoms bound to it. Nitrogen has 3, and oxygen has 2, typically. And in order to understand why that's the case, we can look to the number of valence electrons that each of these species has. So if we look to the periodic table and we can see that carbon has 4 valence electrons. And so there are 4 other places where, 4 other spots on orbitals where bonds can be formed. And again, those could be hydrogen atoms, they could be other carbon atoms, they could be all sorts of other things. If we look now to nitrogen and oxygen, nitrogen has 5 valence electrons and oxygen has 6 valence electrons. So nitrogen has 3 spots where it can bond to something else, and oxygen has 2. You'll notice that both nitrogen and oxygen have electrons that are not bound to anything else. These are called lone pairs of electrons. You can also see that carbon, nitrogen, oxygen all have full octets. They have 8 electrons. We call this the octet rule, but really it only applies to carbon, nitrogen, oxygen, and fluorine, so it's more of a convention than a rule, but it's good to keep track of. So let's look at converting lines to formulas. This is a really important skill in organic chemistry, and you should practice this a lot. So if we look to this first compound on the left, I'm going to highlight where there are carbon atoms and hydrogen atoms with red dots and blue dots. So if we look to the skeleton, we recognize that at each junction there's a carbon atom, and so there are 5 carbon atoms. And the way that these formulas work is that unless something else is drawn on that atom, we fill out as many hydrogen atoms as we can, such that carbon has 4 things bound to it. So at each of these spots we have, in the far left we have 3 hydrogen atoms, on the far right we have 3 hydrogen atoms, in the middle we have 2, and in the very central carbon we have just 1. So if we move over one line structure over to the left, we can see that again we can fill out how many carbon atoms there are. There are 3. There are now 8 hydrogen atoms, and there's an oxygen, so we draw in the oxygen as well. We can do the same type of idea on the next structure. And finally, on the far right we have a ring structure. So when we think about ring structures, this is now carbon bound all the way around to itself again in a ring. Rings, if you're thinking about naming, is actually pretty simple. So you look at how many carbons there are, which we'll see are 6. So it's now the hexane class. To make it a ring, we say cyclohexane. So that's a cyclohexane ring. And another feature I want to point out about these two structures in the middle is that they are actually isomers of each other. And what does isomer mean? If you look to the Greek, iso means same and mer means part. So they are two molecules that have the exact same chemical formula, but they are just arranged in a slightly different way. So reactions that we do in organic chemistry can change the bonding that's found in a molecule. So we haven't learned about this reaction yet, but we typically like to draw this arrow in the middle. A straight arrow between two molecules like this is a reaction arrow, and it goes from a starting material to a product. And again, this particular reaction, it happens to be an oxidation reaction, but we don't need to worry about that at the moment. A few things to note about this is that this molecule has its base unit is propane, so it's 3 carbons, so it has a propane unit. There's an alcohol functional group on it. So if we wanted to name this, we have to look to where that alcohol is bound on the propane. And as it turns out, it's bound to the second carbon in. And so we call this 2-propyl alcohol or 2-propanol. We could also call it isopropanol. There are all sorts of different ways to name, and all of these ways are appropriate. Now, if we look to the molecule on the right, we'll notice something that you haven't seen before, or seen before at least in this class, and that is there are 2 lines between this oxygen and carbon in the middle of the molecule, and those multiple lines means that there's multiple pairs of shared electrons, or also known as a double bond. That functional group that's the carbon with 2 bonds to an oxygen is referred to as a carbonyl. And this particular molecule, again, has a propane base and it has a ketone. That is another name for this particular functional group. That is a carbonyl with 2 carbons on each side. We'll talk about functional groups in a later lecture. So that propane and ketone can be mixed together and say propanone. And that this particular small molecule has a name, a conventional name that we all know this, or most of us know this as acetone. So again, sometimes the names have to do with the exact following a rigorous naming structure, and sometimes these molecules have names just because they are found pretty commonly in our everyday environment.